Thank you for having me here. This talk is based on joint work with Marton Balazs, Timo Seppelainen, and Patrik Ferrari. So I'll be talking solely about the last passage percolation model. This model lives on the setup is on the Z square lattice, so at each weight, so that the weights are distributed in an i.i.d manner, and each one, the marginal is exponential one. Then fix 2 points on the lattice, and then we look for an upright path, such as the blue path in the picture, that goes from A to B, that maximizes the sum of the weights along it. So we look for the upright path that collects the most weight from A to B. We call such a path the geodesic from A to B. The subscript AB denotes the starting and the end point. And this path can be shown to be unique. So that's all right. Okay, so let's denote the weight that's collected along the geodesic by G subscript A, B. And what can we say about this? We call it the last passage time. And what can we say about it? We say that the first leading order is macroscopic, is 4n, and then we have fluctuations of order n to 1/3, where eta here in the perfactor is known to be distributed as the Tracy rhythm distribution, which is familiar from in random matrix theory. There's also a functional limit. So if we fix the point at the origin and the point n, we let n go to infinity, we subtract 4n, then we have these fluctuations, and we know that we converge to the Tracy rhythm distribution. But if we tweak the endpoint along the anti-diagonal that crosses nn at the order of n to 2/3, if we move it like this, can you see my cursor, by the way?
Yes, we can.
Yeah. If you move the endpoints on this anti-diagonal, then you obtain a limit function that is can be decomposed into something that is called the Airy process, Airy process, minus parabola. There are other more complicated limits, functional limits. There's the KPZ fixed point by Metelsky, Kastel, and Remenick, and then there's which you move the endpoint also along the diagonal, crossing from the diagonal from the origin to the point nn. So the idea is that the point along the diagonal direction is as if you go in time, if you change your interface in time. And when you go in the anti-diagonal direction, then you are looking at the spatial changes of the surface. And so the KPZ fixed point is when you look at things in space and time. And the directed landscape by Dovren, Ortman, and Virag is when you sort of change the two endpoints in space and time. But this is we're mostly this is enough for our talk. This is the Airy process. You don't need the more sophisticated functional limits. One more model in this last passage percolation family is the line to point model. This is where you're looking at the anti-diagonal crossing through the origin. Let's call it T0. we assign weights on this anti-diagonal. And again, we are asking what is the upright path starting from T0 and terminating at B that collects the most weight. And again, we call it the geodesic. Okay, so this time we can assign not arbitrary but general weights on the anti-diagonal. And then this would be different initial conditions for the model. For example, we can construct what is called the stationary last passage percolation. So for every row between 0 and 1, we assign i.i.d. weights on T0, on the anti-diagonal, according to the formulas here. So here, when I mean exponential 1 minus rho minus exponential rho, is that this is the distribution of the difference between two independent random variables with these distributions. So if we assign these weights on T0, we obtain the what is called stationary last passage percolation. Now, once you have a last passage in general, you have a last passage model, it sort of endows weights on the edges of your lattice. So for example, you look at the point X, right? So there's this edge to the left of X and below it, right? Two edges. So we can assign weights here by looking at the difference of the last passage time from T0 to X and from T0 to this point, which is X minus E1, just going left. And so we can assign weights on the different edges that are north and east to T0. A crucial point here is that if you take a sequence of edges that constitute a downright path, such as this one here, then these edges, these weights on these edges are going to be independent, and they're going to be distributed according to the distributions here. So if it's horizontal, it's going to be, this is actually reversed. So if it's horizontal, it's going to be exponential 1 minus rho, and if it's vertical, it's going to be exponential rho. Okay, so this is crossed. Okay, and along a downright path, these are going to be independent. Okay. Right, so why is this called stationary in the first place? So as we said, if we are considering anti-diagonal that is north and east to T0, this is just a sequence of downright path, downright path, right? So you can see that the distribution along this anti-diagonal will be the same as the distribution that we assigned on T0 in the first place. Therefore, this is, you can see that there's the kind of a stationarity going on here. Okay, so one interesting point that we will touch on a bit later is that locally, when I say LPP, I usually mean a point-to-point LPP. So locally, LPP looks like stationary LPP. And what do I mean by that? So we had this kind of, we had this functional limit, right? That this i.i.d process, and this is just the spatial changes as you tweak the endpoint along the anti-diagonal. And so we have results showing that this i.i.d process that up to a constant will behave like like a Brownian motion. So the first such result, and I think it's the first one, is by Pimentel, where he showed that if you look closely around the origin, in kind of a functional way, the Airy2 process looks like a Brownian motion. And then there are results by Hammond and recently with Hammond, Covered, and Hedge, showing that if you look at not just locally around the origin, if you look at on a compact interval, then the whole regularity of the Airy2 process will be that of a Brownian motion. So it's as if you randomize the Airy process from the Wiener measure with some change of measure. And also we have recent result from Sarkar and Virag which shows that this also holds for when you start from different initial conditions on the anti-diagonal. So why am I telling you this? Because this shows that why is this, the Brownian motion basically represents so if you remember, if we look back at the increments of the stationary process, you can see that they represent a random walk. In the case that rho is 1/2, this would be a Brownian motion in the scaling limit. And this shows that locally, the point-to-point geodesic, the passage time behaves like the stationary last passage percolation. Okay, so yeah, so this would be, this picture here would be something like the result of Pimentel. So close around the origin, you have the Airy2 process behaves like a Brownian motion, and this would be something like more of the other results of Hammond and the other guys, where the path itself is kind of Brownian. Okay, so next let's focus on geodesics. So one important property of the geodesics is that if we take the 2 points, we have 2 points A and B on the lattice. Let's take the difference between them to scale like n. So the geodesic would tend to follow the straight line going from A to B, in the sense that the fluctuations would be of order n to 2/3. Okay? So it would be very close on a macroscopic scale. It would seem to be very close to the diagonal from A to B. Now, if we fix the origin here and we look at different endpoints, by the uniqueness of the geodesics, we will construct a tree, what we call the geodesic tree. And the question now is, what can we say about this geodesic tree? So let's define things more concretely. So the point-to-point tree, geodesic tree, we will define it to be the collection of all the geodesics starting from the origin and terminating somewhere in a small box that is located n away from the origin. And the side of the box will be delta n to the 2/3. Okay, so we look at all the geodesics starting from the origin and terminating somewhere in the box B delta. And similarly, we do for the stationary geodesic of 1/2, starting from T0, right, and terminating in B delta. And a priori, there's no reason why these two trees should agree in the box B delta. But this is the content of the next result, which is joint work with Marton Balazs and Timo Seppelainen, which says that with hyperradiality, the two geodesics agree, the two geodesic trees agree inside the box B delta. Okay, so let me try and sketch the proof. I'll just give the main components of the proof. So the first thing to do is to take two other stationary geodesics in such a way that they would, with high probability, they're going to sandwich the stationary 1/2, this one, the red one, and the point-to-point geodesic. Okay, so we're sandwiching the two, no matter where we go inside the box B delta. Okay? This, more concretely, this can be done by taking rho minus 1/2 minus some constant r n to minus 1/3, and similarly, by adding a bit, we define rho plus. This will ensure that with probability 1 minus exponential minus CR to the third, is the geodesic would actually sandwich the stationary and the point-to-point geodesics. So we're tweaking a bit the density at 1/2 to get this kind of sandwiching. So this trick is kind of common in many papers. Another thing we need is localization, which basically says that if that we can find an interval, which we call I delta, okay, the interval here. This interval will be very close to B delta, to the box B delta. It will be of size delta n to the 2/3. And we want to show that with high probability, no matter where you go inside B delta, you'll have to cross the interval I delta. Right? So in a way, you can't just go around it and enter B delta. So this would be a localization. And lastly, we need what I would refer to as queuing representation of increments of passage time, which is where we use these results from Marton Seppelainen, which the idea is that one can show that where the blue and the purple geodesics will cross, where they will cross through I delta. So we said that we have bilocalization, we know that they will cross through I delta. Where they will cross in I delta is a function of the increments along that they endow on the on the edges of I delta. Okay, so on each edge of I delta, we have these weights coming from the two stationary passage times. And if we know these, if we know these increments, if we know these weights on these edges, then we can tell where it's going to cross I delta. Well, it's not exactly true, but up to another data that you need coming from here that is shared for both of them. To make this to get to the point is if we show that the edges somehow agree with high probability, the weights on the edges of I delta agree for the purple and the blue, then we show that they leave from the same point at I delta, which would mean that they have coalesced. And since by the first step, we show that they envelope the red and the black geodesics, this would mean that they actually, the red and the black geodesics are coalesced before reaching B delta. Okay?
Can you please repeat what was I delta again?
Excuse me?
What was I delta again?
I delta is an interval of size delta n to the 2/3 that is located close to B delta, to the green box. So I want to sure that wherever, once you enter the B delta, okay, you crossed this small interval.
Mm-hmm.
And because they sandwich these two jobs, the red and the black, if they meet before they reach in I delta, then they must, then the red and the black will have to meet as well because there's sandwich between them.
I see. Okay.
Now, as this is the main bit of the proof, let me dive into. Let me try to explain what I mean by how do we show. Basically, what we want to show is that the weights on the edges of I delta with high probability are equal for the blue and the purple. So yeah, this the way the language in which we approach this is that of queuing theory. So I'm going to talk a little bit about queuing theory. I'm sure many of you are familiar with this, but still, just to jog your memory on this. So what is a queue? So we're all familiar with standing in line for movies or restaurants. We have people standing in line waiting for some service. Let's call them customers. There's a server, someone who gives the service, who attends to the customers. Once they finish serving a customer, the customer leaves. The next person in line approaches, comes over and starts being serviced by the server. Okay. In the meantime, we have customers coming in the queue. Once a customer comes in, he goes to the back of the queue. Okay. And this is pretty much the whole story. We will need a few measurables, a few observables from this story. One is the service time. Service times are simply the time it takes the server to, it's a sequence of times that basically the time it takes the server to serve, a certain customer. Okay, so it's how long it takes for the server to serve the i.i.d. customer. The second thing we need is the difference, what we call inter-arrival times. This is the difference in the times of arrival of two consecutive customers. Okay, so we have two, one after the other. There's a time difference between their arrival, and we'll register that as well. And given these two sequences, from the story that I just told you of people coming in, coming out, we obtain this an output which we call an inter-departure times. It's another sequence, basically registering the times, the difference in the times of departure of each customer. We will assume that lambda is smaller than rho. This would mean that the server is somewhat faster, the rate of service is faster than the rate of people arriving in the queue. And this is simply to just make sure that the queue doesn't blow up. Okay, so mathematically, this is just this. We can sum this, boils down to two inputs. Here it should be inter-arrival times. The inter-arrival times, the service times, and the queuing mapping takes these two sequences. I'm not going to go into there's no point going to the exact mathematical formulation of the queuing mapping. But what it does is basically it takes these two inputs, follow these the steps that I mentioned before, and spits out these the inter-departure times d. Okay, so it takes two independent. So yeah, maybe I didn't mention this. These two are independent. It takes two independent sequences and spits out inter-departure times, another sequence. Okay, so queues can be at stationarity. This is due to Burke in 56. This means that if you have a server that serves with independently and exponentially at rate rho, and you feed the queue with customers coming exponentially lambda, i.i.d., then the departure time, the inter-departure time, the sequence that is going to come out, the output sequence, will be, again, i.i.d. exponentially lambda. In other words, we show that the queuing mapping has a distribution of fixed points. Okay? Right, so lastly, what we need is queues in tandem. That's the last bit need from queuing theory. So if you can take a few servers and just place them one after the other. So, and then you feed the first one, let's say Q1, you feed it with customers, and the output, the departures, inter-departure times will be fed into the next queue, which in turn will feed the Q3 and so on and so forth. Okay, so these are queues in tandem. When we have these one queue after the other, one serving the other. Okay, so now what's LPP got to do with all these things about queuing theory? So LPP here, you can see it's lives on Z square, right? And we said that when you have last passage percolation, any model, you can assign weights on the edges simply by taking the difference between the two endpoints, between the transversal time of the two endpoints of the edge, right? So this is here on the right-hand side, and small you can see like what the last passage percolation is. And if we slice this kind of this ladder-like shape, and we look closely, then we can now sort of turn this into a queuing story by consider this as a queue, okay? Here these would be these weights on the edges would be the inter-arrival times. So if this is the Ji point, this would be the service time of the J customer, of the J customer by the I server. Okay, so these would be the service times, and these would be the inter-arrival times. Okay, and we know that if we have these two sequences, we can apply the mapping, the queuing mapping, and what we'll obtain is the inter-departure times. Okay? And then we call them i.i.j. Okay, so, and then this will be, these inter-departure times can again be fed into the next ladder shape here. And so this would mean that we can again sort of tell the story about how it behaves like a queue, and this shows you that this indeed behaves like a queues in tandem. Is this clear, or maybe I was a bit, okay, I hope this is clear. Okay, so just to give you an example, to sort of take the last passage model, put it back look it through the lens of queuing theory, then the rarefaction case, the point-to-point case. Okay? This will be the case where you have n servers in tandem. The queues will be empty, and you feed infinitely many customers to the first queue. The passage time would be the time where how long does it take the end customer to be served by the end server? Okay? And in the stationary case, this would be just feeding. This now would be like having by infinitely many servers, okay? and where each server is fed by customers coming at rate lambda, and they would be served at rate 1 actually. So rho would be 1. This is the stationary case. Okay. So okay, so now we have these, so if you recall, we talked about these two weights on the edges coming from two kinds of geodesics, the blue and the purple. And they had different rows, they had different densities. And this would mean that by stationarity, the weights that they would endow on the bottom edges, horizontal edges, would be the blue would stochastically dominated the red. Okay, so if we have two rho plus and rho minus, rho plus the weights on the bottom edges would stochastically dominate the red ones. And what this means is that basically you can couple them. Just by definition, you can couple the two sequence of weights on edges in such a way that the blue would be larger than the red, right? This what it means to be stochastically larger than something else. So we can couple them together so that the blue are controlling the red, dominating the red. Then we apply the mapping theory using the same blue weights, the same weights for both of them. And what you can show is, that it can be shown that the queuing mapping preserves order. So at the output, you're still going to have these, or you're still going to see order between the blue and the red. So the blue will still dominate the red the red weights on the edges, which again, these are just inter-departure times, right? But the distribution of these coupled distribution, this coupled distribution here at the output may not be, and this is in general not the case, that this will be the same as the one that we fed the queue with, right? So we chose some kind. We know that there exists at least one way to couple these two, that one dominates the other. But is it true that we will have the same kind of couple distribution on the other end? And yeah, so what we want is to have this kind of a fixed point for phi, but now for joint coupling of these two, joint distribution of the blue and the red together. Okay, so this was solved by Timo Seppelainen. And the way to do it, the way to sort of couple them together is to take two independent sequences, A and S. A would be the arrival time. We will have intensity of 1 minus rho plus. And S will be the service time. We will have intensity 1 minus rho minus. You feed A and S to phi here. And you can show by using by looking specifically, going into the formulation of the queuing mapping, you can see that the inter-departure times will dominate the service times. And what they showed in their paper is that actually this kind of coupling, if you push it through phi again, then it would be a fixed point for the mapping phi. Okay, so going back to how is this helping us, just to conclude this. So we said that we wanted to show that with high probability, the weights on the weights on the edges of I delta coming from the purple and blue geodesics will be equal, right? We want to show that with high probability, that just all the edges are equal, right? All the weights on the edges are equal. But since we know now, we know that we can couple them in such a way that is stationary, and in such a way that we understand, we know that it's a queuing mapping, we understand exactly what's the joint distribution, we can actually compute, we can actually bound the probability that they're not equal, okay? Or not equal on I delta, and this is exactly what we want, right? We want to show that with high probability, they are equal when delta is very small, okay? So this is the way around it. Yeah, any questions? Okay, so next, the next part of the talk, I'll discuss. This is the next part of the talk is work with Patrik Ferrari, where we sort of extended these results. So now fix a point X that is somewhere around the origin. And consider the tree that consists of all the geodesics starting from X and terminating somewhere in D delta. We call this HX, okay? Now, note that D delta is somewhat different than B delta in its geometric, in its geometric dimensions. So the width is the same as before. It's delta n to the 2/3, but the length is now macroscopic. And the reason why this is kind of optimal is because from these KPZ, there's what we call the KPZ exponents, which tell you what's the right way to scale things in order to see something meaningful. It says that these are the n to 2/3 this way and n this way are the right exponents. Okay, so in a way, this is kind of the optimal way to look at things. So we have this tree, okay, and so the next result is with Patrik Ferrari, and it shows that no matter where you start in this blue box, which dimensions you can read off from here. No matter where you start, and the geodesic tree HX will coalesce, will agree on the delta with TS, with the stationary tree. Okay. Now there are a lot of numbers, there are a lot of notations here and equations. So let me just point out what's the difference between the previous. Let me just point out the improvements compared to the previous result. So now we have the geometrics of the whole geometric conditions are optimal in a sense, and they're different. They're improved. So that's one thing. The other thing is the improved lower bound. Before we had 3/8, now we have delta 1/2 with this logarithmic correction. And finally, and quite importantly, there's the upper bound, which had been a bit elusive before in the previous work. And let me just point out how much time. Okay. Yeah. So let me go over what was needed to for this improvement. So for the lower bound, we needed one. The most prominent ingredient, most crucial ingredient that we needed was this property of geodesics to stay in a cylinder of these dimensions of n to 2/3 and length n. And as far as I know, it originates in a paper by Balazs, Geodesics, and Sly on their slow bond paper. so before we said that at a certain point, the geodesic doesn't go too far from the diagonal. This is a kind of a way to argue that it doesn't go anywhere inside for all these points in this box. Okay, so it's kind of a uniform way to bound the geodesic in a strip. The second thing we needed for the upper bound, what we needed is a more careful analysis of queuing, of this queuing representation, of this whole queuing business. Because what we needed now, we needed to show that essentially what we need to show is that the purple and the blue geodesics, when they cross I delta, they cross on different points. Okay, so let's say the purple goes on the left-hand side and the blue on the right-hand side, and in order to force them to sort of break off from each other, we needed to go deeper into this queuing story. Yeah, okay, and yeah, so lastly, let me say something. I need to justify the universality in the title. So let me just say something about the when we have general initial conditions. So we can, as you said before, that we have this line-to-point last passage percolation, where we assign weights on this anti-diagonal. And we can define this tree, we now call it HIC, which is basically the tree that consists of all the geodesic, leaving from this anti-diagonal and ending somewhere in D delta. Okay, so we need to some conditions on these initial conditions, some restrictions. We will require it the exit point, this point here, where the root leaves the anti-diagonal, will require it not to leave too far from the origin. Okay, so this can be captured by Q delta, which is essentially the probability that this distance here is too far from the origin. Okay, so the requirement is that Q delta goes to 0. And so for this, for here, what we can say is that, again with Patrik, is that with high probability, the two trees the stationary and the initial condition one would agree in D delta. Okay, and so here we have this correction of this going too far from the origin. So yeah, I think I went too fast. Okay, so sorry for the, yeah, pretty much done.
Okay. Thank you, Ofer, for the nice talk. So if anyone has questions, they can unmute themselves and ask. So I have a question, like in the result with Patrik Ferrari, you considered the box A, right? So can you go back to the slides?
Wait, oh yeah, the first one?
Yeah. So you can choose any point X inside that box. It doesn't matter.
In A delta?
Yeah.
Yes, yeah.
Okay.
So in order to get these optimal, we need to, yeah, at this moment, so in a way it would be nicer if you could say something about two points, I mean, it's another way to put it, but 2 points that are very close to each other on 2/3 order to show how that decays. So the results of Hammond about non-existence of these two disjoint of like two geodesics starting close with two close endpoints, and the probability that they do not coalesce. So to have something like that in that sense, we need to sort of squish the blue box, and that would be another way to would be a nice way to sort of represent this result. But for that, we're missing a few. We need to improve the techniques, the current techniques. We need something new for that. So in a sense, in order to get these exponents, this one half, basically we have the right exponent for this event, right?
Yeah.
So in order to say something about when this set is very small, we need something. We need new input.
Hi, I have a quick question. Just on the last slide, when you're doing the general boundary with the stationary version, I was just wondering how was the argument with the two perturbed parameters, like how is that coupling argument done when you're doing the general data with this?
Which slide are you referring to?
Oh, the last one, just the one you're comparing the general data with the stationary boundary. Yeah. So so does the same technique apply here, like where you have two perturbed parameters, and then you do something, you trap the two, like the two paths between the two perturbed boundaries.
Exactly. So it's as long as you're staying very close to the origin, the perturbed ones would sort of come out far from the origin and would sort of encompass these two geodesic and make sure that you have this sandwich. But if you know that there's no upper bound here, right? So this goes back exactly to what I was saying, that we need something new for this.
I see.
Because
yeah.
Here you can HIC can be very concentrated around the region, right? So we need something for the upper bound, for example. We need something which is the same thing as what I said about the big box.